In Module 4, the circuits that were analyzed or designed did not have any particular structure. The number of flip-flops were small. Now we'll look at circuits that have more structure with multiple stages or cells that are identical or close to identical. This makes expansion very simple. Registers are particularly useful for storing information during the processing of data, and counters assist us in sequence processing. A register is a set of flip-flops, possibly with added combinational gates, that perform data processing tasks. The flip-flops hold data and the gates determine the new or transformed data to be transferred into the flip-flops. A counter is a register that goes through a predetermined sequence of states upon the application of clock pulses. The gates in the counter are connected in a way that produces the prescribed sequence of binary states. Although counters are a special type of register, it is common to differentiate them from ordinary registers. Registers are useful for storing and manipulating information. Counters are employed in circuits that sequence and control operations in a digital system. The simplest register is one that consists only of flip-flops without external gates. Here we have a register constructed from 4 D-type flip-flops. The common clock input triggers all flip-flops on the rising edge of each pulse, and the binary information at the 4 D inputs is transferred into the 4-bit register. The 4 Q outputs can be sampled to obtain the binary information stored in the register. The clear NOT input goes into the R NOT inputs of all 4 flip-flops, and it is used to clear the register to all zeros prior to its clocked operation. We maintain clear NOT at logic 1 during normal clocked operation, allowing it to be logic 0 only when a system reset is desired. The transfer of new information into a register is referred to as loading the register. If all the bits of the register are loaded simultaneously with a common clock pulse, we say that loading is done in parallel. Here is a symbol for the register we just discussed. This symbol permits the use of the register in a design hierarchy. It has all inputs to the logic circuit on its left and all outputs from the circuit on the right. The inputs include the clock input with the dynamic indicator to represent positive edge triggering at the flip-flops. Most digital systems have a global clock generator that supplies a continuous train of clock pulses. The pulses are applied to all flip-flops and registers in the system. If we want to leave things unchanged, we can prevent the clock from reaching the clock input. To do this, we use a separate control signal to control the clock cycles during which clock pulses are to have an effect on the register. This approach can be implemented with a load control input combined with the clock. Inserting gates in the clock pulse path produces different propagation delays between the clock and the inputs of the flip-flops with and without clock gating. The clock signals arrive at different flip-flops or registers at different times, and we have something called clock skew. To have a truly synchronous system, we must ensure that all clock pulses arrive simultaneously throughout the system, so that all flip-flops trigger at the same time. For this reason, in routine designs, control the operations of the register without using a clock gating is advisable. Here we see a 4-bit register with control input load that is directed through gates into the D inputs of the flip-flops instead of through the C inputs. This register is based on a bit cell consisting of a 2-to-1 multiplexer and a D flip-flop. The signal EN selects between the different data bit D entering the cell and the value Q at the output of the cell. For EN equal 1, D is selected and the cell is loaded. For EN equals 0, Q is selected and the output is loaded back into the flip-flop, preserving its current state. The register is implemented by placing 4 D flip-flops with enables in parallel and connecting the load input to the EN inputs. When load is 1, the data on all 4 inputs is transferred into the register with the next positive clock edge. When load is 0, the current value remains in the register at the next positive clock edge. The transfer of information from inputs to register is done simultaneously for all 4 bits during a single positive pulse transition. This method of transfer is traditionally preferred over clock gating, since it avoids clock skew and the potential for malfunctions of the circuit. A digital system is a sequential circuit made up of interconnected flip-flops and gates. To specify a large digital system with state tables is very difficult, if not impossible. This is because the number of states is prohibitively large. To overcome this difficulty, digital systems are usually designed using a modular hierarchical approach. In most digital systems, we partition the system into 2 types of modules: a data path, which performs data processing operations, and a control unit, which determines the sequence of those operations. Control signals are binary signals that activate the various data processing operations. To activate a sequence of such operations, the control unit sends the proper sequence of control signals to the data path. The control unit, in turn, receives status bits from the data path. These status bits describe aspects of the state of the data path. The status bits are used by the control unit in defining the specific sequence of operations to be performed. Data paths are defined by their registers and the operations performed on binary data stored in the registers. Examples of register operations are load, clear, shift, and count. The movement of data stored in registers and the processing performed on the data are referred to as register transfer operations, which are specified by the following three basic components: the set of registers in the system, the operations that are performed on the data stored in the registers, and the control that supervises the sequence of operations in the system. An elementary operation performed on data stored in registers is called a micro-operation. Examples of micro-operations are loading the content of one register into another, adding the contents of two registers, and incrementing the contents of a register. A micro-operation is usually, but not always, performed in parallel on a vector of bits during one clock cycle. We denote the registers in a digital system by uppercase letters, sometimes followed by numerals. These indicate the function of the register. For example, AR is an address register, PC is a program counter, and IR is an instruction register. The individual flip-flops in an input register are typically numbered in sequence from 0 to n-1, starting with 0 in the least significant position and increasing toward the most significant position. Since the 0 bit is on the right, this order can be referred to as Little Indian. The reverse order with bit 0 on the left is referred to as Big Indian. The most common way to represent a register is by a rectangular box with the name inside. The individual bits can also be identified as shown in Figure B. Data transfer from one register to another is designated in symbolic form by means of the replacement operator, or the arrow. The statement you see here denotes the transfer of the contents of register R1 into register R2. Specifically, the statement designates the copying of the contents of R1 into R2. The register R1 is referred to as the source, and R2 is referred to as the destination. By definition, the contents of the source register do not change as a result of the transfer, only the contents of the destination. We can also have conditional transfers. Normally, we want a given transfer to occur not for every clock pulse, but only for specific values of control signals. This can be specified by a conditional statement symbolized by an if-then form, where K1 is a control signal generated in the control unit. In fact, K1 can be any Boolean function that evaluates to 0 or 1. Here you see two forms of this statement. The basic symbols we use in register transfer notation are listed in this table. Registers are denoted by an uppercase letter, possibly followed by one or more uppercase letters or numerals. Parentheses are used to denote a part of the register by specifying the range of bits in the register or by giving a symbolic name to a portion of the register. The register transfer language used in the book differs from both VHDL and Verilog. Here you can see all three notations side by side for comparison's sake. Thanks as always